Good afternoon and welcome back to our Unity mini-series. We're back with episode 2, and today we're going to look at movement and collisions. So you can download Unity Hub if you haven't, and it actually saves a bunch of versions. So if you look at my installs, I have various versions here. I'm using 2020.2.1. It's not the latest, but it's just the latest is 2020.2.2. You can use that one as well. It should work pretty much the same. But I'll be using that in my project today. So let's get started. We just create a new Unity project. I'm going to make it 2D because we're making a 2D project. And I'm going to call this Unity Miniseries Tutorial. I'm going to create it and I'm going to wait for it to start up. And I'll fast forward to when it does start up. Okay, it took me a while, but we're finally in. So you might notice that my layout is slightly different from yours if you use the default layout. So actually, under Window, under Layouts, you're probably using this default layout. What I do to change my layout a little bit that people are curious about is I put the Project tab here, the Console tab here, change the Project tab from 2-column layout to 1-column layout. Then I add several windows. For example, I add the Tile Palette window, put it at the right side. Then I add an animator window, and I put that up here. I close the Asset Store tab, and I add the animation window, and that should be about it, pretty much. So that's my layout. And if you go under Window and Layouts, you can actually save your layout however you want. I've saved it here. So pretty much you can see it's almost identical. I guess the animator tab is usually up here for me. Yeah, so there we go. So when you load into the sample scene, one thing that I like to change is the main camera immediately. I just change it to like a slightly darkish gray to near black color because I do not like the classic blue background. And then let's create some objects. So you can look under 2D Object Sprite. And right now we don't have any real sprites, so we can actually create that under Assets, under Sprites. There we go. Square. And I'm just going to leave it a square for now. So I'm going to rename the sprite to Player. I'm going to tag it as a player. It's on the default layer, but I'm just going to add a layer that says Player. This is just good practice to do. And then I'm going to put it under the player layer. I'm going to reset its transform. And then I'm going to set its sprite to be the square that we just created here. And now that we have the square, it should be basically one unit perfectly. So if you look at the units that Unity has made, it's pretty much one unit. And so we can color it slightly differently if you want to. I'm going to just pick this slight green color. And that's our player. Then we can create another 2D object, another sprite, reset its transform. We can use the square for that as well, but we'll make this a slightly different color. Maybe let's pick some bluish color, like that. And we'll call this platform. And we'll tag it. We'll add a tag. We'll call it platform. Save that. Go back to the platform and then add the tag to it, and then again add another layer. Same thing that we did with the player. So all this is preliminary setup. I'll have a link to some of the project materials and scripts in the description below, so don't worry about it too much. We can resize this platform however we please. Then we can just add a box collider to it. Box collider 2D specifically. And that should be good to go. And that's our platform. Our player will be adding some scripts and stuff later, so we can actually press Control D, that's D as in Daniel, to duplicate, or actually D as in duplicate, that's actually what it's used for. And then you can make other platforms, and maybe we can press Control D to duplicate again. Maybe something else. It's just to kind of design a level. It doesn't have to be anything good for now. This is just to test out things. Yeah, maybe this is your test level. Just gotta adjust that. Looks pretty decent. Maybe not something that you'd find in an official game, just a test environment. And you should be good to go there. So let's create a script now. So as you go down there, you can go under Create and C# script. We're going to name this Player Controller. And we should be able to open this up in Visual Studio. This also is going to take a little time, but oh, we're lucky today. Visual Studio is opening up faster than usual. Oh, there we go. Okay, so the first thing that most tutorials don't tell you is that you can create a namespace. So the reason you might want to create a namespace is because other people can have scripts named player controller as well. This kind of uniquely identifies your own sort of script. So if I label this namespace as CPP Game Dev Club, you can name this whatever you want. It's just a space containing my script under this name, like CPP Game Dev Club. So you can name it whatever you want. So this is something I encourage you to do when you're making any new script. Next, we're going to add a component menu. Now, what the heck is this? Most people don't talk about this either. So I'm going to label it Unity Miniseries / Player Controller. I'll show you in just a second. So if you have this and save it, and you go back to your scene, you go to Player, you do Add Component, and you have this list of all the components. If you have an artist, for example, that never uses a programming scheme, they just want to add it to themselves. Oh, look, now there's a Unity Miniseries component, and under there you can add a player controller. So I'm not going to add it just yet. There's one more line of code that I want to add. and that is require component. And basically, what that does is it requires a type of component. So in this case, we want the player to have a box collider 2D. Without that, the player cannot work. So since we want that first, we can require that, and watch this. When you go under Unity Miniseries and add the player controller, it automatically adds the box collider 2D. So whenever you have certain things that you want to access in the script, for example, if you want an animator to be accessed in the script, you might want to require a component, which is a type of animator. So we want to require the box collider 2D because we'll be referencing it in the script. So any components that you want to reference, you want to require them. That's another important thing. So now that we have that, let's get some variables in here. So let me just delete these comments because we don't need those. And so firstly, we can initialize a private box collider 2D, and we can name this box collider. So this will help us remember. And we can have a private bounds. So this will be the bounds of the box collider. So if you go back here and you look at the box collider, honestly, I shouldn't have picked green. Maybe I should have picked another color. Let's make this slightly yellowish, or like slightly orangish. The reason I picked green was because I wanted to use red raycasts, and red and green contrast each other pretty well. But I guess this is fine too. So now when you go to this player, and then you look at the box collider, you can see the bounds. Those are the bounds of the box. So generally what you have is a minimum X. Let me just move this to a better location. Minimum X, minimum Y location, as you can see with my mouse. A minimum X, maximum Y. A maximum X, maximum Y. And then a maximum X, minimum Y. So those are the 4 points right here. And we'll be using that to determine how to raycast and what point to raycast from. And then you also, one last thing you have is a center X and center Y. So we need all those things, and I'll show you in a bit in Paint how we're going to structure that. But until then, that's what the bounds are. Next, we want a range. So this is something else that might be new to you. A range from 2 to 20, or 2 to 10. Let's do that. And serialized field. These two things might be new to you, and I'll explain in a second. Each ray count. So essentially what this is doing is it's saying there will be something from 2 to 10. You have a slider from 2 to 10, and serialized field means show it in the Unity inspector. So if we go back to our player, and oh wait, first we should save the script so that it compiles. Go back to the Unity inspector, and look, you have a slider, goes from 2 to 10. And it's called hrate count, and I'll explain that in a second. But it limits it, and it also shows it even though it's a private variable. Private variables are normally not shown in the inspector. If you have something public, it's normally shown in the inspector. So it's a good practice to keep things private because you don't want other people to access your data. So since we want to keep this private, to show it in the inspector for testing, serialized field is how we do that. So we can do the same thing. Let's copy this line of code and then paste. This time we're on to 2 to 20. Honestly, this is supposed to be V-ray count, and this is supposed to be H-ray count. And now you might ask, what the heck are V-ray count and H-ray count? Well, when we have any sort of box, let's say, that represents our player, we're shooting out rays to test if there are collisions ahead of us. So if there's something here, we want to make sure that it's detected. And the same thing vertically. So horizontal rays, we want to keep the count of them. Maybe we want 10 horizontal rays. Maybe we want 5 vertical rays, something like that. So usually, since your player is more of a rectangle most of the time, so let's make the scale, or instead of the scale, yeah, actually, yes, let's make the scale so that the person's 2 units tall, 1 unit across. Usually you'll have a player like this because they're humanoid, so they'll be longer than they are wide. And because of that, you want more horizontal rays and then fewer vertical rays, because the taller your player is, the more you want to detect. And the shorter your player is, the narrower your player is, the less you need to detect. And you need a minimum of 2 because you need at least like the 2 corners so that you can detect from there. So now that we've determined that, we need to keep a count of how many that we want. So that's why it's V-ray count for vertical ray count and H-ray count for horizontal ray count. We have those variables in here, which we'll use at some point. Next, we want a private float, H-ray spacing, and V-ray spacing. And then H-ray length and V-ray length. So we can save all of this as one line. And essentially what we're doing here now is determining all these different aspects. We just want to keep track of all of these things. This is the spacing. So we want to measure that because we want to determine how far away each ray has to be created so that we can shoot out the rays. And then the length. So how long the ray is supposed to be. So this is the length. So we're just keeping track of everything. So now that we've added that to the variables, another thing you might want to have is serialize field, and you might want a private float of the move speed of the player. So the move speed will allow the player to move at a certain speed, and we want to serialize it so that we know, okay, maybe he moves like 5 units or 2 units fast. So depending on how fast you want him to move, that's why we set the move speed there. Then we can have a private float, which is the velocity. Actually, I think that should be a vector 2. Yeah. Private vector 2 velocity. Private float. That is gravity. So we can set this to like -20 for now. Let's just keep it whatever. We'll mess with that later, that value later. So let's keep that around -20. Then private bool is grounded. So this will tell us if we're on the ground or not. And then this, oops, my bad. Private raycast origins, ray origins. So now this is something that's going to be new to you. So there's no such thing as a raycast origins component or item or anything. We're actually making this up. So this is something that we're creating on our own, and I'll get to that in just a second. Just a couple more variables. It looks a little complicated and overwhelming, I know, but it'll start making sense as we go through the code. Raycast hit 2D, hit, and what else? We should serialize field for private layer mask. Layer mask. All of this stuff will slowly make sense as I explain it. And yeah, that should be it for now for the variables. We might add some more later. So for now, let's create the raycast origins. So what are the raycast origins? So that's where your raycasts all originate from. So in the intro video, if you remember, every raycast has an origin and a destination. So if you have this line, this is the origin, this is the destination. Now, since we know the length and they're only horizontal and vertical, we technically know the destination. So we don't really need the destination. We just need the length and the origin point. So knowing those two things, we can get every ray that's vertical and every ray that's horizontal. So if I have, this is my collider, let's say, the bounds of the collider are these essential points that we can get. So this right here is the min.x, min.y. This is the max.x, max.y. And then we can just to give you an idea of some other points that we can determine. This is not min, sorry. Center.x, min.y. So this should make sense. This is center. This is a center of your x coordinates, right? And the minimum of the y coordinates. So if you have an axis of an x and a y coordinate axis, minimum, maximum, center, all this stuff should make sense in an x and y coordinate system. So that's the same thing over here. I'm just drawing it without an axis. So the reason you might want to know this stuff is because we want to know the origins. So raycast origins, that's what we're finding out. So why do we need the raycast origins? Well, if you have this square, right? If you have just this point, you have every horizontal ray from this point. This is the coolest thing ever. So what you do this is the bottom, right? Raycast origin. And from here, let's say you give it a length that goes to the right. Well, there's one ray. Then you add some horizontal ray spacing. Then you can go to the next ray. And it adds on. It adds on. And you keep adding some spacing. And it keeps going up. So all you need is this for all the horizontal rays. And then if you go to the left, you get all the horizontal rays to the left. So left and the right, you get it from just this one point, bottom to top. And you can do the same thing for vertical rays. But all you need is this point. Basically, from here, you can go upwards, adding some vertical ray spacing. So from here, if you go downwards, get vertical ray spacing in this direction. So all you needed was the spacing, the count, the length, and the origin. Those are the key features you need to cast a ray in any direction. So these are the only 2 points you actually need, the left and the bottom. So that's exactly what we're going to do. So we have this struct raycast origins. We can actually make this private struct. And under here, we actually, to access it within the class, we can make public vector2 left and bottom. So just like I said, the left and the bottom are the only 2 points we need. And a vector2 can either mean a vector or it can mean a point, as you can see in the description here, representation of 2D vectors and points. So those are the 2 points, the left and the bottom. And we're going to set them later. So there we go. We just built a structure that we created ourselves. So raycast origins didn't exist before. We made this containing these 2 vectors. So now that we have this, what we can do is we can initialize the start method. And what we do is we get the box collider by setting box collider equal to get component box collider 2D. So essentially this gets the box collider 2D, and this is exactly why you want the require component line of code, because it makes sure you have the box collider 2D. Next, you want to calculate the ray spacing. So the reason we do that is because we want to know the distance between all the rays. So this we can make in a quick method below called public void calculate ray spacing. So how do we calculate the ray spacing? Well, first we want to do something called set bounds. So this isn't something that, this is another function that we have to create because we want to make sure we know what the bounds are. So we can make another function called set bounds. And essentially, it's only one line of code, and all it's doing is it's setting the bounds to equal the box collider dot bounds. So since we initialized this first, we already know it's referring to the box collider, so we just set it to the bounds of the box collider. So after we set the bounds, we want to set the V-ray spacing to equal the bounds dot size dot x divided by the V-ray count minus 1. So looking at this, it looks a little scary. And then you might look at this and say, why the x and not the y? Because it's V-ray vertical. So if you actually look at this, the vertical rays, you're actually taking the bounds of the size of the x and then dividing it up to get the spacing between the vertical rays. So the spacing itself actually uses the x, but the vertical rays themselves are using the y. So spacing is x, and it's vice versa for horizontal rays. So spacing here will use the y. So essentially what you're doing, you're taking the whole thing and you're dividing it up. Now, there does come one problem. So if you have the ray go from the exact bottom, when it collides with something under it, it starts throwing different problems and starts becoming very wonky. So what we're actually going to do is we're going to shrink the range a little bit so it's a little less than the whole bounds. So actually what we're going to do is we're going to do bounds.size.x minus 0.2 and once we shrink it by that much, we just divide it, and basically what it's doing is it's taking 0.1 amount from each side, so 0.2 total, 0.1, 0.1, and then it takes this distance right here, this amount, and then divides it based on the count. So if we have 10 rays, then we have 9 spaces, for example. And then, so if we go back to the code, it'll be 10 minus 1. So the count minus 1 is how many spaces you have. And that's essentially how we get the spacing. So we set the count right here. But the spacing occurs in the math over here, so we actually don't need to show the spacing as something to mess with. And we can do the same thing with h-ray spacing. But this time, like I said, it would be bounds.size.y. And same thing, minus 0.2f. And we divide by the h-ray count minus 1. That's pretty much it for the ray spacing. Going back to our start method, we want to set our velocity to 0. So velocity equals new vector 2. We'll just say it's 0, 0. We don't have to do this, but it's just a good idea to initialize like the important variables that you're using right away. And then we can move on to the update method. So the update method involves setting the velocity first. So the velocity in the x direction, it equals input dot get axis raw horizontal and multiplied by move speed. So essentially, this is just the x, it takes the horizontal axis, which means we can press A or D on the keyboard or the arrow keys on the keyboard, left and right. And it'll put that in the x vector. And we're multiplying it by the move speed that we're going to define here. So we can just define that right away. We can say something like 5. And it's not really going to do anything if we play with it right now, because it's not actually setting the player's velocity to that move speed yet. It's just giving that move speed there. And then we can say something like if you're grounded, if is grounded, if you're on the ground, then the velocity dot y equals 0. Otherwise, we can say velocity dot y plus equals gravity times time dot delta time. And gravity is -20 as we defined earlier, and it's just consistently adding to the velocity because we always have gravity being added. And and if it's grounded, then we don't have it added. So let's actually check everything first before setting the velocities. So after we check that, we set the velocities. And finally, we can, we can move according to the velocity. We can pass this in. So let's make a move function. Public void move. Oh, not unanimated move, just move. And we're going to pass in a vector 2, which is the velocity. So now that we have that, the first thing we want to do to move is we want to calculate the rate origins, because we want to detect collisions before moving. So first we want to calculate the rate origins. We already did the spacing at the starting, and the only reason you'd calculate the spacing is if the box collider itself changed. Like if you were crouching, maybe you resize the box collider, then you have to recalculate the spacing. But the origins, you have to calculate always when moving, because as you move left and right, you don't want to keep the origins in the same spot. You don't want to keep this. If you move to the right, then you want to move the origin to the right. And if you move to the left, you want to move it to the left. So that's exactly why you want to calculate the rate origins. And we don't have a method for that, so let's make that really quickly. So public void calculate rate origins. Okay. So first, what we want to do is we want to set bounds. We just want to do this for safety. And then second, we can say rate origins dot left. So we define rate origins up here as a raycast origins object, and we have a left and a bottom. So we want to set the dot left, and over here, I'm going to set the origins dot bottom. So the dot left equals the new vector 2, and that it should be the bounds dot min dot x and bounds dot center dot y. And the same thing, but this time it's bounds dot center dot x and bounds dot min dot y. It should make sense based on how it is. The bottom is the center here, center of the x and the minimum of the y. The left is the center of the y and minimum of the x. So hopefully that made sense up to now. So we just calculate that first. And we also calculate the bounds because it's always moving. So once we calculate the ray origins, we want to make sure is grounded is false. And then if the velocity dot y is less than 0, well then we want to do a ground check. And we're going to pass in a reference to our velocity. And then finally, after doing all that, we're going to transform.translate by our velocity. And we should be good to go. Oh, we do want to multiply our velocity times time dot delta time. Yeah. And the ground check, it doesn't exist yet, but essentially we can just create that really quickly. Public void, ground check. So this ref key term, what that means, what is ref? Well, ref just means it affects the velocity directly. Normally, when you have a function, it'll make a copy of the variable and change it in there, but it won't return the variable itself change. So a reference makes sure the variable itself changes, so the velocity itself will change. So that's what ref does. So transform.translate velocity. Now, technically this isn't doing anything, so based on what happens here, you're probably going to see this guy fall infinitely through the floor. There you go. And you also saw, if I move left and right on the keyboard, that should work as well. So right now, we don't have him colliding with anything. That's why the ground check is there. So we can start filling this in to make sure that he doesn't mess up. So first things first, let's get the length of the vertical ray to be the ray origins dot left dot y. So we get the y of the left minus the bounds dot min dot y. I'll explain this in just a second. Plus mathf dot absolute value of the velocity dot y. Going to here. Generally, how a game works is that you have frames. So one frame runs, you go to the next frame, and it updates something. So what happens is your character, when he's falling, right, with gravity, let's delete this. When he's falling with gravity, he has a certain velocity. So what we want to do is we want to stop him when he touches the ground. The issue is we don't want to stop him right when he touches the ground, because by the time the frame processes and the next frame runs, he'll go through the ground a little bit. So he might actually be stuck in the ground, or there might be other problems there. So what we want to do instead is cast a ray that has a length of his velocity added to this length right here. And basically what we're doing is this velocity right here, we're going to move him by that amount on the next frame. So it'll actually be accurate because it won't force him to move on the same frame. It'll make him move on the next frame by that velocity amount. Okay, so this length right here is the mathf.absolute value of the velocity in the y direction. So why do we do absolute value? Because if this length was negative, then it would actually subtract, making it go take away from this length. That's why we did the absolute value. And then this length right here is just rateorigins.left.y minus bounds.min.y. So this .left.y minus the min.y, this length right here. So once you get that added to this, you get the total length of your vertical ray. There we go. Next, what we want to do is make a for loop. And what this is going to do is it's going to iterate through how many we want. So we want v-ray count. So in this case, that would be 10, I believe. Got 10 vertical rays. So it would do from left to right, it would generate the rays. So that's essentially what we're doing in that for loop. And we have to do I++, so that it iterates through them. Next, what we have to do is we have to set hit equal to physics2d dot raycast. So this is actually what's doing the raycasting. It's checking if it hits something. So that's why we named it hit. And what are the things that you pass in here? Well, you need an origin. Well, look what we did. We created an origin, rate origins dot left. But each time we iterate, we want to increment by a certain I. Okay. So what we want to do is we want to add a new vector 2 to that. And basically, we want to move it to the right by v-ray spacing. We want to move it by that much times I, because if it's 1 away, then we want to move by 1. If it's 2 away, then by 2. And we keep going down by that. And then we also want to add it by the velocity.x, because we might be moving left and right in midair. So that's something else that we want to add to that. So that should be it for the origin, right? The direction, well, since we're doing a ground check, we know that we're moving downwards. Down. The length, it's just v-ray length. Oh, not v-ray spacing, v-ray length. And the layer mask. This is the last and most important thing. So we actually created this layer mask up here. And essentially, why we made the layer mask is because we want to set it to platform. So it should be colliding with the platforms. That's what the layer mask does. It determines which layer you should collide with. So putting all of that together, we save that in this hit variable that determines if it hit or not. And what we can do is actually draw an array of that. So we can actually copy this part right here. The origins.left, blah, blah. Can draw that. And then a direction. So we can say vector 2 dot down times v-ray length, because we want that length. And a color. So I'll do color.red. You can set this to whatever colors Unity has in its code type base, but I just want to show that this is visible. And this should draw right away. So this isn't still going to stop you because we didn't set it to stop. But, oh, I didn't, one thing that's happening is maximizing on play. Second of all, the gizmos aren't turned on. So when the gizmos are turned on, you can see that there's actually the rays are there. So one thing that I made a mistake of is the left should add 0.1 because we shrunk it slightly, if you remember right here. So we want to start 0.1 in. And the same with the ray origins dot bottom, you want to add 0.1 to this. That should even it out. And if I run this again, yeah, it's more in the center now. Yeah. So now that we have the rays, we want to do something with this hit variable. So once we hit something, what do? Well, if we hit, so that's the cool thing, you just need to say if hit, then the velocity dot y should equal negative 1f times, so why is it negative? Because we're going in a negative direction for the ground check, we're falling, times the hit dot distance, so it's the distance from here to the floor, so that's the distance. And then we want to subtract from that, actually it's the total distance. So basically, if you have this as your player, the hit dot distance will be from here all the way to the floor, wherever you detected the floor. So this is the distance. What you want to do is you want to subtract this part from it, and that'll give you this right here, and that's the velocity you want to move the player. So to subtract this, what you have to do is you want to take the bounds.min.y minus the bounds, bounds.center.y minus the bounds.min.y. So bounds.center.y is the bounds.left.y. So we can do hit.distance minus, in parentheses, ray origins.left.y minus bounds.min.y. And that gives us the velocity that we have to move the next frame. Then we can set the V-ray length. This time we have to readjust that, and that'll just be this short distance. So why are we setting it to this? Well, we want the V-ray length. Now that we know that we're going to be on the floor, we just want the length to be this. We don't want anything below that. We don't want to go anywhere below that. So we set the V-ray length there. And finally, we want to set is grounded to be true. So now that we know that it's true, if it's grounded, the velocity is 0. So that means the gravity won't constantly accumulate to like negative infinity, so you'll kind of stop. This should work. Yeah. So there you go. So you see this little problem here when you go left and right into walls. It'll start getting confused and kick you forward, up and down into weird places. So that has to do with left and right collisions. But as of now, we have the ground collisions. So that's the important part. Now that we have this, we can literally just extend this by copying and pasting and changing a couple values. So we can paste this right here. And instead of ground check, this will be the ceiling check. This will check if you're hitting the ceiling of something. And this time we have the bounce.max.y max.y subtracted by the ray origins dot left dot y. So the reason that's the case now is because if we're checking upwards, right here, this is the max minus the center, which is the ray origins dot left. So that's how you get this length now. And still adding the velocity.y. The thing that changes here is vector2.down is now vector2.up. V-ray length, layer mask, it should still all be the same. Raycast, ray origins dot left. Seems to be right. This would be up times V-ray length. And essentially, this now is not moving in a negative direction, so we can take this out. And this isn't ray origins dot left minus bounds dot min. It's actually bounds dot max minus ray origins dot left. You can just paste that here and here. It essentially works the same way. I'm not going to go and explain every single one because it's basically the same thing reiterated for the ceiling check. And all this code will be available if you are a little confused. So is grounded is now, let's say, is above. And let's make a quick private bool. So we have is grounded. Let's do an is above, is left, and is right. So we'll have all four of those. And essentially at the starting of the move, you want to make sure all of these are false. Above equals false. Is left equals false. Is right equals false. And honestly, you could do something like reset collisions or something. This might actually work better. Something like public void reset collisions. Instead of having all these 4 lines of ugly code, you could cut them and paste them inside this function, and then just call reset collisions. And essentially, you can say if the velocity dot y is greater than or equal to 0, we can do a ceiling check, passing the velocity. So maybe you want to do this before. So this here. So this should work technically speaking, but we can only check that once we get a jump in. So for now, we will keep this. We will keep this how it is. We can do the left and right the same way. And just copy this and paste right here. We can do .x and .x here. Instead of ceiling check, we'll say left check and then right check. Or if it's greater, then it should be right check. And finally, left check. And those don't exist, so we can copy the ground check. And since this has a little bit more changes, I'll adjust the left check and then copy it for the right check. To the left. Now this is slightly different because now we have to look at the h-rays. So h-ray length. So this starts from a different perspective. So over here, let's take this. We start at the bottom this time and then go left and right all the way up. So to get the distance, we want to take the max minus the center. So going back to that, it equals this is the left check. Okay, so it's actually the min or center minus the min. So it would be ray origins dot bottom dot x minus the min dot x plus the absolute value, the velocity dot x. So that should work for the left, and then this should be the h-ray count instead of the v-ray count. Then if you're casting a ray, you want to start at the bottom. You want to add a new vector with h-ray spacing instead, times I plus, you don't need any other velocity added to it because we've already done that in the vertical one. And the second thing is you want to adjust the y, not the x. So it's 0, comma, h-ray spacing times I. So now that you have the y value being changed, you're going up, up, up. So each ray will go higher. Once you have that, each ray spacing times I, then now you're going to the left, each ray length, and layer mask. That should pretty much, we don't need this debug dot draw ray. This was just to show us. Yeah. So we'll keep that empty for now. If it's hit, the velocity dot x should now equal, since it's left, -1 times hit that distance minus ray origins dot bottom dot x minus bounds dot min dot x. Copy and paste this again. And finally is, oh, sorry, not is grounded, is left equals true. So this should work for if we have left collisions. There is an error. The name right check doesn't exist. Oh, yeah, this doesn't exist yet. So let's just comment that out just to test it. Going back. There we go. The left should work. Yeah. See? So the left works, the right still doesn't work. Then the vertical collisions should technically work. Okay. So now that we have that, finally, we can just copy this and paste for the right. So we'll call this right check. And the only thing we have to change here is mainly this part. So this will be bounds dot max dot x minus ray origins dot bottom dot x. Then we can copy this, change it here, change it here. Make this is right. And then all the V's have to become H's. Okay, I don't know why it didn't change, why it still worked even though I didn't change this to H. So H ray length velocity dot X. Now this -1 isn't there because you're moving to the right. This should pretty much work. Dot bottom plus new vector to, okay. This just needs to be changed to right. H ray length, everything is H. And X's, except for this Y. Yeah. We should be good to go on that front. Okay. Oh, there is still some sort of issue. Oh, I know the issue. It's still commented out. Silly me. Okay, let's go back. Let's test it one more time. Should work now. Yeah, there we go. Now, time for the last thing in this tutorial. Oh, there's a slight issue there. Hopefully, that won't cause too many problems. I don't know what that is. Last thing we want to do is the jump. Okay. So we'll change the update method. So we'll say if you're grounded and you press, let's say, the space bar, you can change this to whatever you want. You can, instead of dot space, you can put dot Z if you want the dot Z key, or you want the Z key, or the dot X if you want the X key. Anyways, I just made the space bar, and then we can change it so the velocity dot Y equals some jump velocity and this jump velocity can be another variable that we set here. So we'll say private float jump velocity. So normally what tutorials do, they adjust the jump velocity and they adjust gravity, or they'll have the gravity in the rigid body. This is not how we generally think as players. Normally what we want is the jump height and the time to the jump. So normally what we really need are these two serialized fields. And those are private float jump height and private float jump time. So this is much easier to understand because you might say, I want my character to jump 5 units high in half a second. So that determines if the jump is floaty. So if you have like a 1 second jump, it will feel much longer and that'll make it feel more floaty. And if it's high, it'll make it taller. The height will give you an idea of exactly where you want your character to be. So how do we get the jump height and jump time based on the gravity and the velocity? Well, we want to set these and affect the gravity and velocity to be based on what we want the jump height and jump time to be. So this is where we use two math equations that you might have encountered in your physics class. You might have never wanted to touch physics in, but here they are. Delta y equals 1/2 at squared plus vit. So the initial velocity times time plus the acceleration times 1/2 times the time squared equals delta y, which is like the distance. And this is one of the kinematics equations. And another equation is Vf equals Vi plus At. So the initial velocity plus the acceleration times time equals the final velocity. These are two of the equations we'll need, the only two that we'll need. And really quickly, it's just basic math. Delta y is the jump height. So the jump height equals 1/2 times A is the acceleration. The acceleration is gravity. So I'll just replace it with the letter G. T is the jump time. So we already, these are the two variables that we need. Jump time squared. And then the initial velocity, we don't have an initial velocity, it's just 0. So it's slowly simplified to this small equation. We're trying to solve for the gravity because we set the jump time and jump height. So it's actually 2 times the jump height divided by the jump time squared. And that equals G. So we already got the gravity. Now that we know the gravity, this equation is done. All we need is the jump velocity. That is Vf. So the jump velocity just equals Vi, which is, again, 0, plus At. So At is just gravity times jump time. And since we came up with gravity already, we can just plug in gravity here and multiply by jump time to get the jump velocity. So we can do this directly in the start method because these values shouldn't change throughout your game. So we just set the gravity equal to negative, because it's a negative value, 2 times the jump height divided by, so this is how you do powers. So we want to do jump time to the second power, jump time squared. And that should be the gravity. And then the jump velocity will equal the gravity, but this time, since we want it to be positive, let's take the absolute value of the gravity and multiply by jump time. And that essentially should set it based on what you want the jump height and the jump time to be. So if you set these in the Unity inspector, go back to the player. Let's say the jump height is about 5 units and the jump time is about half a second. Or let's make this like a little lower. That's a little high for jump, 4 units. Now, if I press the space bar, there we go. It jumps about 4 units in half a second. And the gravity and the velocity are adjusted to fit that. And as you can see, when you hit the vertical collisions, it should make you stop. So I see that there are a couple bugs here, and we'll get them sorted out in the workshop. But for the most part, you have a working raycast controller that more works than a rigid body controller because of how little of the physics engine it needs, and essentially based on certain values like velocity and time and gravity that you set yourself. There could be some things like continuous collision detection and stuff like that. So otherwise, there might be a few optimizations that I'll look into, but that should be good enough for a Raycast tutorial. And I'll put the code up. I'll I'll see if there were some errors, and I'll let you guys know in the comments. Thanks for watching. If you liked this video, please make sure to give us a thumbs up and subscribe. Give us any suggestions down in the comments below, and we'll try and cover them in the future videos. See you in the next one.